So we're gonna finish looking at that problem that we started today in strengths. And a couple of things we want to review is when we are talking about rigid body rotation, as I have this lever here and I pull down with my hand at E, this bar is going to rotate rigidly about pin B, and we're going to end up with a displacement of cables that looks something like similar triangles. Okay. The next thing I want to keep in mind is if I were to draw a free body diagram of this system, I have tension in my cables, my force is pulling downwards. I always have to remember at B, I also have the internal forces acting at that pin in the X and Y direction. Okay, so if I were to sum forces in the Y direction, I have three unknowns. If I were to sum moments about, let's just say this one, I still have three unknowns. And so we're gonna learn about how to have an additional set of equations when it's an indeterminate system like this is, and we can look at compatibility of deformations. And one way we're gonna do that is to look at how we have the rotation and how we have similar triangles to relate. So this is actually a pretty important lesson. So the first thing we're gonna do is we're gonna kind of talk about small rotations. It's small strains. We don't want large deformation. If we do have any rotation, we want it to be minimal. Okay, we don't want to see that. And because we have such small rotations, which is such small strains, we can kind of simplify things. So if I have a rotation of theta equals 2 degrees, I want to convert that to radians. And the way that I do that is pi over 180. The way I remember that is a full circle is 2 pi. It's also 360 degrees. Okay, a half circle is pi, which is the same as 180 degrees. So I just kind of use this relationship, which is this one divided by 2. So if I have degrees and I need it in radians, I know it's pi over 180. If I were given radians and need it in degrees, I'm just going to rearrange 180 over pi. Okay, but this is how I remember it. 180 degrees is the same thing as pi, or 360 is the same as 2 pi. So I can convert my 2 degrees to radians. And then I can just take this delta C. This delta C is equal to the perpendicular distance from where I'm rotating times this 2 degrees in radian form. Okay, so I can just take 0.3 meters right here, 0.3 meters times 0.03491 radians, assuming small strains, and I get that I have a displacement of 0.01047 meters, which is the same as doink, 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 10.47 millimeters. Okay, so this right here, this displacement is 10.47 millimeters. And how do I know this to be true? Well, if I want to look at this triangle, I can say that tan theta is opposite over adjacent. So I have delta C and I have that adjacent value. So tan of 2 degrees has to equal delta C over 0.3. Okay, I can rewrite this 0.3 times tan of 2 theta, and I get that delta C is 1.0476 times 10 to the negative third, which is indeed 10.47 millimeters. Okay, so using small strains, I just convert the angle and then multiply by that distance, and I'm going to get the same value. Now, where I need to consider this is because I have this rigid body rotation, if delta C is 10.47 millimeters, which is now blurry. See if I can get this back on here, right? Okay. There we go. If this is 10.47 millimeters, this is rotating at the same 2 degrees. So I can set up similar triangles all across, and our reference point is our pin. Okay. So I'm going to have delta A is to 200 millimeters as delta C is to 300 millimeters as delta D is to 500 millimeters as displacement at E is to 300 plus 200 is 500 plus whatever this little nugget is. So let's just call this 200 millimeters. So 2, 3, 4, 5, 6, 7, 8, 9. So we have this neat little relationship from similar triangles. And now that I know the displacement at C, I can calculate the rest of these because the displacement at C is 10.47 millimeters. So now if I want to know A, I can cross multiply 10.47 times 200 divided by 300. Okay, 10.47, 200 times 300 divided by, and I get that delta A is 6.98 millimeters. I can do the same thing here. If I want to know delta D, okay, I can cross multiply and then divide, and I get 10.47 times 500 divided by 300, and I get 17.45 millimeters. So now, when we start looking at indeterminate, which is going to be, I believe, chapter 4, I now have this relationship of being able to compare my displacements up and down to how far away I am from that rotational point at B. And that's called similar triangles.